Go. So today's lecture is going to be fairly easy. It's just building on previous concepts that we've learned. We are going to have about 3 practice questions just to kind of iron things out with you guys. Let me actually take attendance fairly soon, actually. So in our previous lecture, we talked a lot about the positive and negative sides of when binary compounds form, right? So we had one side of a binary compound that will be a fractional negative, and the other side of a binary compound being a fractional positive. And today we're actually going to visualize, we're actually going to visualize what that actually looks like. So we're going to have a center of positive charge and a center of negative charge. So this is primarily for ionic compounds, but it can also be applicable to polar covalent molecules as well. Right? And this time, like I said, we're going to get a little bit more visual about it. So we're going to have an arrow represent this dipole moment, in which the base of the arrow is going to be the positive side, and the tip of the arrow is going to be the negative side. It's actually pretty standard procedure for many science classes. We always want to be going from the positive side to the negative side. So HF, as we all know, is a very strongly ionic compound, right? And so we will absolutely have a pretty strong dipole. Some other ways of visualizing this, we've got our H2O molecule as well. And as we can see here, we've got a fractional charge once again. This time the oxygen is going to be sucking up all the electrons, causing them to become negative. And notice how even though it's kind of a 2D geometric situation, we can still interpret this as a linear dipole moment arrow. So instead of having a dipole moment like that and a dipole moment like that, we can have a kind of like a center of mass situation, which a general positive side will point to a general negative side. Over here, we've got more of a CG generated diagram that shows the various electrostatic potentials of this entire region. So I'm going to leave this slide up for you guys, and I'm going to take attendance. Like there's a couple of people missing. So yeah, hopefully that all makes sense. Right? Notice that this this negative plate and this positive plate, these actually represent parallel plates of an electric field, right? So the water molecule in an electric field, this would also line things up, right? Very similar to what we did in a previous slide. Just in case you guys were wondering what that was. We've got these parallel plates. So a negative side will attract the positive end, positive side will attract the negative of our binary compound. And in this case, our compound looks linear, but even with more complex geometric shapes, we can more experimentally discover what is the positive side and what is the negative side. Okay. Now, sometimes we might have no dipole moment, right? So our dipoles are going to cancel out. And you can probably guess that that often happens if we have the same elements tied to each other, like N2, O2, whatever, Cl2. But it also occurs if there's just a balance, right? If there's a balance between a negative ion and a positive ion or a portion of the molecule, then these guys are going to cancel out completely equally. We've got 180 degrees behavior, right? And so this time our carbon is going to be super positive because the O values are still a little bit more negative. We look at our EV values. Computer generated 3D space. CO2. Next up, we're going to talk about metallic bonds. Now, this is kind of different from the situation of covalent and ionic bonds because even with most covalent bonds, there's a bit of an unequal sharing of electrons. However, in metallic bonds, there's so much sharing going on that these electrons are not necessarily even tied to any of our atoms, right, or any of our nuclei. Okay. So because these are all pure metal elements, we recognize that there's no difference in their EV values. Okay, we can just say that they're metallic. So anytime that we see a compound that just has a pure, metal element listed, we don't really need any other additional information. Okay, we already know that we're dealing with this sea or cloud of electrons floating around all of our various nuclei. So Ag, as we all should know, is basically silver. So this is the structure of silver. And this is how we represent it in a diagram. Notice how these electrons are just kind of being shared completely even. And so therefore, these are not really strong bonds, I would say. So a little bit more about that. We've got a bunch of free electrons being shared, especially in their shells, right? So these would be more of the valence electron shells. So in this valence electron zone, they're constantly moving around. So they're still somewhat well packed together. Okay, we've got our positively charged metal cores because, again, on average, each of these atoms is kind of losing an electron too. That's why metal ions tend to be cations, positive. And like I said, we kind of want to describe this as a sea of electrons floating around the surfaces of these nuclei. And this gives a big hint as to, the properties of metals. You guys have all dealt with metals in real life. You recognize that, they have things like electrical conductivity, right? Electricity is very easily able to pass through them, right? Malleability. What is malleability? Right? We want to cut through it with a sledgehammer. We can actually do that very easily if it is a pure metal, purely transition metal. Okay, and low volatility just basically means it does not react very easily, right? It's got very high boiling points. It's got very low freezing points. Actually, I should say high boiling points and melting points. Although that depends on the metal. So here we've got pure sheets of gold. And as you can see, we're cutting through it with a scissors pretty simply. And this is why when you buy gold jewelry, it's never fully pure gold. If you were buying pure gold jewelry, it would break apart pretty easily. So that's why these industrial engineers, they will tend to combine gold with other metals or elements in order to strengthen the material. So all this is just to say that we do not really have much of a dipole moment involved when we're dealing with these sheets of metal. Any questions? I know this is a quiet class, so we are moving rather quickly. You guys know this stuff already in terms of like why pure metals are malleable. If you're lucky in your chemistry class, you might be able to do some experiments with pure transition metals. We are definitely going faster than the previous class, but we'll go ahead and try out some example problems here. And hopefully that means that you are understanding it very easily. Let's try drawing a few dipole moments. Okay, so for each of these following elements, let's determine the orientation of the dipole moment. If there's a. So I'll give you guys about 3 minutes on this one. It is pretty easy. If you need me to rewind back to previous slides, just let me know. But I am hoping to see about 4 to 5 responses at least for this chat box.
I have a question. So for the negative and positive charges, how do you like determine like what it is? Is it just like which one has a bigger electronegativity?
I mean, yeah, because they will be pulling the electrons more towards them, right? So maybe this is a better example. So since we know from the EV charts, which I think I showed, I mean, this one you should know. Where's the EV chart? I think right here. Right, so the ones with stronger electronegativity, they are going to be able to pull in those electrons a little bit closer to themselves and away from the other atoms which are on this side.
I see. Thank you.
So that is what determines the other shape. And I know you guys can't really draw this stuff in the chat box, but you can still describe what the arrow looks like. Especially part B, that should be kind of easy. So. 4 to 5 responses, and he's so far off that line. So I hope everybody's still with me here. Couple responses, thank you, they're accurate. We'll give another 30 seconds before I make the big reveal. Going to interpret this as being too easy for people. But we're going to recognize that our iodine is going to have a stronger electronegativity than hydrogen because it is further to the right. And so therefore our arrow is going to be pointing from the hydrogen, which is more positive, to the iodine, which is has more electrons. Our N2, as you can guess, since it is both of the two of the same element, it's not going to have any dipole moment whatsoever. So that pretty much concludes our business with the dipole moments. We do want to now care about electron configurations and maybe a more advanced perception of electron configurations, depending on how stable we want to make our compounds. Okay. So whenever atoms do react with one another, they tend to share electrons in such a way that they reach, both atoms will reach a noble gas configuration. Can anybody remember what a noble gas electron configuration looked like? Maybe like the last term. Right? It involved being in the P zone. And if our P zone was fully filled up, then we would achieve peak stability. So I'll probably draw this out for you guys. Whoops. So P6, remember, it looks something like this. We've got our free spaces, and we're going to fill up this first space, and the second space, and the third space. So if all of those are filled up, we'll have a P6 formed, which means we've got 8 valence electrons on the outside. So neon, I believe, has 10 electrons total, or I don't remember. It's actually a smaller number. 6, 2, 2. It should be 10 total. So yeah, so we've got the 8 valence electrons on the outside and the 2 in the inner core. Right? And it doesn't matter whether it is neon or argon or radon, whatever it is. All we're recognizing is that since this is a stable configuration, even atoms that are in different locations within our periodic table can actually kind of move towards that zone, depending on how many electrons they gain or how many electrons they lose. So in general, if we have 2 nonmetals, which are, nonmetals, which are on the right-hand side of our periodic table, they will always form a covalent bond. Remember, because the EV values, the delta EV, is going to be very small. So these covalent electrons are going to be shared such that they complete an electron configuration, filling it up to be 8 total valence electrons for both. So, you know, if one atom is 6 and the other is 6, they're going to borrow, I think, 4 total electrons would be shared so that they each have 8. Okay. So what that means is they're kind of moving to the right. So with these nonmetals, they're kind of moving a couple spaces to the right. They're going from P4 to P6, or they may be going from P3 to P6. I think I'm going 1, 2, 3 spaces to the right. And that will determine the number of electrons that are shared between the 2 atoms. What happens if we share with a metal? So if a nonmetal and a transitional metal react, well, what will tend to happen is that the valence electrons from the metal are going to move towards the nonmetal. So the electron configuration of the nonmetal will move on to the next, will appear to be like the next noble gas. Whereas the metal, the transition metal, is going to move backwards, quote unquote, to be the previous noble gas. Let's double check on a definition here. I want to make sure that these are transition metals and not representative metals. So give me 1 second. Oh, transition. Okay, so these should be. I'm gonna actually edit this a little bit because it's not quite edit. So non-metals and alkali/earth metals react. So these are the metals, quote unquote, that are all the way to the left side of the periodic table. Those metals will actually move backwards to reach the noble gas of the previous row. So the valence orbitals of the metal, which is usually just S1 or S2, those are going to be emptied out. They become positive, and you'll end up with your common binary compounds, such as salts. So let's look at some examples of what that looks like. Let's say, for example, we've got calcium and oxygen, which are going to react with one another. Well, the calcium has a shortcut, and that's going to be argon, and then we move on further down the rows to 4s2. This is 2 outer electrons. Oxygen, its previous noble gas is helium, since it's higher up on the periodic table. So it's going to go 2s² and then all the way over to 2p. So when these two guys react with one another, okay, they're going to combine to make something that's going to look like P6. Okay. How do we know which way they're going to go? Well, obviously the EV value of oxygen is very strong, whereas calcium, since it's far to the left, it's going to be very weak. Right? So what's going to happen is that the oxygen ion is going to pull the electrons from the calcium ion. It's going to slap onto here and cause a 2p6 business to occur. So we have these 2 extra electrons from the calcium moving on to the oxygen, and it will cause these ions to split up into Ca2 plus and O2 minus. Okay, if that does not make sense, I would make sure that the periodic table is by your side so you can take a look and kind of recognize the pattern. Questions? So this leads rather smoothly to the concept of isoelectronic series. Hopefully everybody knows what the prefix iso means. So iso just kind of means the same, right? They're trying to standardize. So if iso means the same, electronic means probably the number of electrons in an atom. That means any series of ions or atoms that have the same number of electrons will be considered an isoelectronic series. And honestly, for the most part, these are all going to be ions, right? So because it's the ions that have lost or gained electrons in order to achieve some stable number of electrons. So because noble gases will very rarely need to gain or lose electrons, those are the only ones that would just be atoms, right? It's everything that's around, right, to the left and to the right of our noble gas that is going to be losing or gaining electrons. And as we implied in the previous slides, it would be the metals, these alkali earth, mineral metals. They're going to be losing their electrons, while these halogens and the other folks on the right-hand side of the periodic table, they will be absorbing those electrons. So we are kind of saying the same thing over and over again, right? We're recognizing that oxygen and fluoride, they are going to be more electronegative. So they will tend to appear more negative since they will tend to have more electrons surrounding them when they become stabilized. And the opposite will be true for the mineral metals on the left side. So the mineral metals are going to be losing electrons so they can appear like the noble gases above them. whereas the nonmetals are going to be gaining electrons so they can appear like the noble gases to the right of the point. So this should really require a bit of a visual here. To be honest, I should include a periodic table here. Hopefully that helps. I don't trust that everybody has a periodic table by their side. So I'm going to slap this on. Any questions? Back to the concept of atomic radii. We've already talked about periodic trends within the periodic table in terms of atomic radii. Ionic radii is going to follow some very similar patterns. But this time, instead of the atoms being fully stable neutral atoms, we're going to look at what types of isoelectronic series form. And the electron cloud will actually be influenced by the positive or negative charges. So as you can see here, we still have the radii increasing as we go down the table. Right. But now as we go left to right, it's going to be a little bit more funky because these nonmetals are going to be very negative, gaining lots of electrons, while the metals are going to be very positive since they're losing electrons. And so therefore the radii are going to increase with the number of electrons in the orbits. This is because they will tend to have electrons in more higher outer level orbits. So these numbers will basically represent the distances of the radii. So if we wanted to order these from largest to smallest, we'd say that SC2 in this series, I guess, is larger than VR, which is still larger than RB and larger than SR2. Notice which ones they chose. This is an isoelectronic series, right? We're still talking about an isoelectronic series. So therefore, they're going to choose these guys and these guys. Okay. Since the noble gas that is being surrounded by these ions is going to be, and the one for this in VR is KR, so krypton. So krypton is the mother noble gas representing all these other ions. So these metals are going to move to the left, the non-metals are going to move to the right. Questions? Let's check out this sample problem here. This one is a little bit in-depth because they do ask you to get a little creative. We just want to make sure that you understand the concept of isoelectronic series. So here, technically, we've got 4 ions. So we want to choose alkali metal, like earth metal, noble gases, and a halogen, so that they constitute an electronic series, isoelectronic series. And obviously, you want to make sure that they're in the most stable configuration. That means we want to get them into the P6 zone. Once you've written out the electron configuration, for each species. You don't have to do it for each species. I would use maybe just the shortcut, just do the last section, right? I also do want you to figure out what is the number of electrons for each species and also the number of protons for each species. So which one is going to be the same, which one is going to be different. That's also, these top two bullets, they're kind of more of a conceptual question than anything else. So I am actually going to rewrite this. A little messy. For and you could choose from any row that you like. Just choose whichever one's easiest for you, unless you want to do more exotic. And I'll give people, this one's a little bit of a longer one. I'll give people 5 minutes to come up with answers to these. Much enthusiasm here. So I'll just try to explain what's going on here. So the electron configuration, you should be choosing just one halogen. Okay, so that could be like, what's an example of a highly reactive halogen? I guess chlorine, right? So you can choose Cl. Right next to Cl is the argon, just the noble gas. Then we go to the next row, and then we choose potassium and calcium seem to be on the next row. Okay. We want to make sure that the potassium is a +1, calcium is a +2, and Cl would be a minus. And so in reality, all of these electrons would have the same number, right? Would have the same number of electrons in each, since it is isoelectronic. Right? The number of protons, however, would be different, right? So that's the identity of the atom, is the number of protons that it has. So it'd be something like, 19 protons, 20 protons, 21, 22, just in order like that. Although I did not really check the exact number of protons that chlorine has, but the idea is that it would be different for protons as it is for electrons. Any questions? Sounds like we all understand this 100%, which is very nice. Again, we want to talk about the properties that periodic tables help us understand, right? So we've gone through a lot of trends up until this point. We've gone through the concept of atomic size, the concept of ionic radius, right? Those are two different things. Ionization energy, electronegativity, those two things are actually very closely related, tied together. It can help us determine the electron configurations. Right, we had the S zone, we had the P zone. Sorry, we had the S zone, we had the D zone for the transition metals, and then the P zone for our non-metals. And using these EV values, we can predict what the formulas would look like for ionic compounds. And those same EV values can be used to determine how strong are these covalent bonds. So are the covalent bonds, totally delta equals 0 for the EV, or would there be a little bit of polarity and unequal electron sharing between the two atoms? Questions with that? Hopefully people are comfortable with if the textbook gives them some more complex problems, they can use periodic tables to make kind of predictions. Right? And so make sure that that Bible is always out there for them. All right. Let's try our last example problem before getting into the final concept here. I want you guys to rank these ions from smallest to largest. So take a look at our, if you want me to rewind back to the previous periodic table that involves, the atomic radii of various ions, I can do that for you. But I think the concept should have, been internalized fairly easily. So part A should be fairly easy. Part B is a little bit more of a challenge because we have to recognize multiple trends. So I'll give everybody a couple minutes to put these in order. And this time, since the question is so easy, I do expect to see some responses in our chat box here. So just put it in order from smallest radii to the largest radii in both sections. to tackle part B as well. The difference between SE and the TE, that's going to be the challenge. Slight change. And I'll reveal the answer to part A very soon. I'll give people another minute to see if they agree with the responses. And I'm going to reveal part 1 at least. Any disagreements between SE and the TE? So I don't really know what TE is actually. I think SE is selenium. Right. Nobody has any disagreements? Yes, indeed, TE is going to be larger than SE. Now, why is that? TE is further down the periodic table, and our periodic trends are still going to be valid in these situations. So when in doubt, use our standard periodic trends information to figure things. We've got our final section here. We might actually wrap up a little bit early. We do have models of covalent bonds, and we're going to talk a little bit more about covalent bonds next time because they are a very important type of bonding phenomenon, right? But we just want to recognize that models are simply simplifications of what's going on in the world. Right? So this tetrahedron structure is what's caused by the CH4 methane compound. Right? Sometimes we can replace the H with a Cl, in which case the Cl would be even, I think, a little bit even more negative than the carbon. Right? But chemists will just draw these things out as they proceed, right, through experimentation. So when developing these models, we just want to be aware of a handful of things that models do not necessarily equal reality. And why is that? Because they are simplifications of, they're simplifications so that we can work with them more easily in our experimentations. Okay? So this is more related to lab work and experiment work. Yeah. So they are often wrong. This could be very relevant to biopharmaceutical industry, right? We're trying to put things together. Hope it works. Sometimes it doesn't. But as time goes on, our models will become more complicated and also more accurate as time goes on. And however more complicated of a model we use will depend on the sensitivity of the task we are trying to perform. So if we're doing a sensitive experiment in the lab, we want to make sure that we know what are the assumptions in the model that we are making so that we don't have any human errors when we conduct our experiment in terms of what we expect outcomes to be. It's also often really good that models are incorrect, right? Because we'll then learn from our mistakes through additional experimentation and application of higher level technologies. So I think this might have been actually a DNA molecule, right? The DNA, the structure of the DNA molecule was kind of, debated for several years throughout the 40s until I think about 1955 was when they came up with the model, and soon after that they determined it was accurate. So this will actually help us internalize the concept of covalent bonds later on. Any questions? So tomorrow we're going to kick off the concept of bond energies. Feel free to take care of any CK12s that we went over during these last few slides. You can even do the CK12s for next session as well, for the next topic as well. Are there any last minute questions? You can hang around for a bit. No, easy. Okay, well, I will let you guys go, and I will catch you tomorrow morning. Have fun, y'all.